systems of pair of linear equations in two variables, and I am going to count the number of solutions. See, as we discussed in the last class, if we have a single linear equation in two variables, it has infinite solutions, whereas if we have a pair of linear equations in two variables, there is one solution, okay, and we will find that solution using any one of the usual methods like elimination method, matrix inversion method, Cramer's method. Okay, we discussed about the matrix inversion method and Cramer's method specifically in the last class. Okay, and now we are going to identify the number of solutions if exist or not, okay, for the given pair of linear equations. Just look at the first situation. This is 2x minus y is equals to 4, and here it is x plus y is equals to 2, and easily we will calculate on adding that y will get cancelled. You left with x is equals to 2 and y is equals to 0, and here in the first case your solution is that x is equals to 2 and y is equals to 0, very clear. Whereas coming to the second case, we need to look at the solution equations first. 2x minus y is equals to 4 is one equation, 6x minus 3y is equals to 14 is the other equation. Just have a look. 2x minus y is equals to 4 and 6x minus 3y is equals to 14. See, if you multiply the first equation with 3, what will happen? If you multiply first equation with 3, it is clearly gives us that 6x minus 3y is equals to 12. Right. So first equation is simply nothing but 6x minus 3y is equals to 12. But whereas in the second equation it is given that 6x minus 3y is equals to 14. So when you conclude these two, it is very clear that 12 is equals to 14 is given as a system of linear equations. But 12 is equals to 14 is not possible, right? And that's why we need to conclude it like a contradiction. Okay? Right. Whereas coming to the last case, see 2x minus y is equals to 4, one pair of equations. 4x minus 2y is equals to 8 is another equation in the pair. And see, you just multiply first equation with 2 and it directly gives us that 4x minus 2y is equals to 8. See, this 4x minus 2y is equals to 8 is again just as the second equation. See, actually if you look, they look like two equations, but if you analyze, if you think, these two are just simply nothing but only one equation. Is that right? But to find a solution, we need a pair of linear equations, but here we have just only one equation. Okay, that's the first part of analyzation. And now when you coming for the number of solutions, this system of pair linear equations has x2 and y0, so we have unique solution in the first part, unique solution. Whereas in the second case, see 2x minus y is 4, 6x minus 3y is equals to 14, and we have a contradiction here, that in the sense this system of equations, pair of linear equations are not possible actually. So in this case we don't get a solution, so number of solutions are 0 here, and we say it as no solution possibility. Whereas in the last case, see actually if you look, there are two equations, but if you analyze we have only one equation. One linear equation in two variables will generate infinite number of solutions as we discussed. So in this case we have many solutions, or you may say infinite solutions. Okay, many solutions, or you may say infinite solutions. So at the end if you analyze, so in one case the system of equations have unique solution, in the other case the system of equations have no solution, and in another case the system of equations have many solutions. And as I mentioned you, every linear equation represents a line, right? So when you think from the geometry wise, see these two equations will represent two lines, and in the first case, since they have a unique solution, these two equations will represent two lines on the graph, and those two lines are specifically intersecting, and they have one intersecting point, and that point is the solution. Okay, so for the equations which have unique solution, its graphical representation is intersecting lines. Whereas coming to the second case, since we have no solution in this case, if you sketch the lines of these two equations, those two lines are parallel on the graph sheet. For parallel lines we know that there are no common points, right? And that's why the graph of these two linear equations is just like parallel lines. Whereas in the last case, since these two equations are simply nothing but one equation itself, and that one equation will generate many solutions. And if you sketch the graph of these equations, see those two lines are coincident. If you say this is the first line, then other line again lies on the same. So we say that here the lines are coincident. Okay, just for the space I am not writing there. Okay, you just think that. Okay, in the first case the equations represent intersecting lines. In the second case the equations represent parallel lines, and in the third case the equations represent coincident lines. Since the two lines are coincident on one another, for sure there exist many common points, right? Because they are coincident, there are many common points, and those common points are simply many solutions. And in this case we have no common point, so no solution. Here we have one common point and one solution. Okay, and in another way, if a equation has a solution, if a equation or a system of equations have a solution, then those type of equations are mentioned as consistent equations. If a system of equations or if a problem will, if it not generates a solution, then we call that problem, that equations, as inconsistent equations. Okay, not only for the linear equations, anywhere. Okay, it may be quadratic, it may be cubic, it may be any number of linear equations in any number of variables, anywhere. If solution is possible, we call them as consistent, and if solution is not possible, we call them as inconsistent. If you think in such a way, then this first case we have unique solution, so these equations are mentioned as consistent equations. Okay, these equations are mentioned as consistent equations. And in the last case again we have a solution, not only one, we have many solutions. That in the sense solution is possible and the solutions are many, so we call these equations are also as consistent equations. Whereas in the second case, if you say we don't have a solution, since these two equations have no solution, we call these two equations as inconsistent equations. Okay, just think once. Okay, basically we are discussing with an example, and in the next thing we are going to generalize it. Okay, right. And the next case, if you look at the equations once again, in the last case itself, the first equation is 2x minus y is equals to 4, and the second equation is 4x minus 2y is equals to 8. That in the sense, if you multiply first equation completely with a constant, it will generate the second equation. Once again I am repeating, if you multiply one equation with a constant, it generates the second equation. That means second equation is completely dependent on the first equation. Once again I am repeating, second equation is completely dependent on the first equation. Since the second equation is depending on the first equation, these type of equations are also mentioned as dependent equations. What? Dependent equations. And since these equations are mentioned as dependent equations, then automatically these equations are independent. Okay, this pair of linear equations are independent equations, as well as this pair also independent equations. Just look at once again. Okay, see, basically it is very easy to solve a pair of linear equations in two variables and finding the solution by elimination method or by using matrices methods like matrix inversion or Cramer's. But we need to analyze how many solutions are there and what are different terms and terminology related to the pair of linear equations in two variables. In the first case, if you look, this system has one solution. So I say it as unique solution, and since it has one solution, the lines are intersecting, and since solution exists, we call it as consistent. If solution not exists, we call it as inconsistent. Okay. And in the second case, this system has no solution because we have a contradiction. Since it has no solution, this system represents a pair of parallel lines on the graph, and since there is no solution, we call them as inconsistent equations. And in the last case, okay, there we have two equations actually, but they looks like only one. If you analyze, it represents a pair of coincident lines. So in the sense, the lines are coincident and they represent many solutions, and since solution exists, we call them as consistent. And in the last case, this second equation is completely depending on the first, and that's why we call it as dependent equations, and these two cases are mentioned as independent equations. Okay, so basically when you are thinking from the side of dependent and independent, see, if the second equation is completely depending on the first, we call it as dependent, other two are independent. When you thinking from the side of consistent and inconsistent, if solution not exist, it is inconsistent, and the remaining two cases are consistent. Okay, just have a look. See, all this analyzation is just related to the linear equations in two variables actually. What we need to extend these ideas for the linear equations in three variables, and that is where that will become easy when you are confident related to this analyzation. Okay, and once again you just go with an observation. See, these two equations have unique solution. That's all clear. Okay, right. When you observe these two equations, you just say the ratio between the what x coefficients of these two equations is 2 by 1, okay, and the ratio between the y coefficients of these two equations is minus 1 by 1, and the ratio between the constants is simply 4 by 2. And if you analyze, this 2 by 1 is not equals to minus 1 by 1, and which is not equals to 4 by 2. Okay, so the ratio between the x coefficients and y coefficients and constants are not equal. And whereas coming for this, you need to observe that the ratio between the x coefficients, which is 2 by 6, right, and the ratio between the y coefficients, which is minus 1 by minus 3, whereas the ratio between these two coefficients is 4 by 14. And if you analyze, this 2 by 6 is 1 by 3, and this minus 1 by minus 3 is also 1 by 3, but these two ratios are not equals to 4 by 14. Okay, whereas if you analyze in the last case, the ratio between the x coefficients is 2 by 4, and the ratio between the y coefficients is minus 1 by minus 2, and the ratio between the constant terms is 4 by 8. And if you analyze, this 2 by 4 is 1 by 2, minus 1 by minus 2 is 1 by 2, 4 by 8 is still 1 by 2. So if you analyze in the last case, the ratio between x coefficients, y coefficients and constants are same for many solutions case, and the ratio between x coefficients and y coefficients are same, which is not equals to the constants for the case where it has no solution. And in the first case, if it has unique solution, these three ratios are not equal. Okay, here in this example, actually these two become equal actually, 4 by 2 and 2 by 1 is 2, but in generally if you take, these two are not equal. Okay, see, first of all we need to pay our concentration on this ratio between x coefficients and y coefficients. Okay, for unique solution case, ratio between x coefficients and y coefficients is not equal, and for the remaining two cases ratio is equal. And then to decide whether it is no or whether it is infinite, we need to check it with the constant ratio, and if it is equals to constant ratio, it gives us many solutions. If it is not equals to constant ratio, it gives us no solution. And now I am going to extend this idea of checking the ratio between the x coefficients, y coefficient and constants to the general form. Okay, I will take two general equations, right, and then I will check these ratios, and from there I will decide about the unique solutions, no solutions and many solutions possibility. Okay, just have a look. So just look at the general form. If I have a pair of linear equations in two variables, simply you say a1x plus b1y is equals to c1, a2x plus b2y is equals to c2. And now I am going to check, okay, related to these equations, whenever they have unique solution, whenever they have no solution, and whenever they have many solution. To decide that, I need to go with the ratio between their coefficients. Okay, see, if all the three ratios, ratio between x coefficients, ratio between y coefficients, ratio between constants, if the three are not equal, then we say that in this case the system has unique solution, the lines are intersecting, the equations are consistent, or as well as you may say independent. Whereas in the second case, the ratio between x coefficients and y coefficients are equal, which is not equals to constants, then in this case we say that the equation has no solution, parallel lines, inconsistent and independent. And whereas in the third case, if the three ratios are equal, in this case we have many solutions and coincident lines, we say them as consistent because we have many solutions, and directly it tells us that the equations are dependent. Okay, so in generally, if I have a pair of linear equations and the question may tell you that this system of equations has many solutions, then I need to use this ratio. If the question tells us that the system of equations has no solution, just I need to use this ratio. Okay, like that we are going to solve some problems. Okay, so usually in previous years also related to this, we are getting one or two questions from the previous papers also. Okay, just have a look. And then now I am going to convert this idea into matrices. After converting this idea into matrices, and then we need to analyze number of solutions for the pair of linear equations in three variables again. Okay, just have a look. Just look at the word. We are going to convert these three cases into matrix generalization. Okay. See, first of all, this is the given system of linear equations, and it is its matrix form. We say it as Ax is equals to B. Right. First of all, you think about matrix A. What is matrix A here? It is clear, I think so. A1, B1, A2, B2, right? And since the matrix A is A1, B1, A2, B2, what to say about its determinant? And it is we are very familiar with the determinant of that matrix A. See, determinant is simply what? A1, B2 minus A2, B1, right? And A1, B2 minus A2, B1 value, whenever it is 0, whenever it is not 0, you just think about the equations and say. In this case, if you say A1, B2 is equals to A2, B1, so its determinant will become 0. In this case again, A1, B2 is equals to A2, B1, so the determinant of A will become 0. Okay, whereas in the first case, A1, B2 is not equals to A2, B1, so the determinant of A is not 0. So, in the first case, we need to say that determinant of A is not equals to 0, and here determinant of A is equals to 0, and here again determinant of A is equals to 0. Okay, and when you think from the Cramer's method side, in Cramer's method we define three matrices like delta, delta 1, delta 2. And among those, the delta is simply nothing but the coefficient matrix A1, B1, A2, B2. Okay, once you revise that delta, delta 1, delta 2, right? So this delta is nothing but the coefficient matrix. So here the delta is determinant of that coefficient matrix, delta not equals to 0, and here delta is equals to 0, delta is equals to 0. Simply delta and determinant of A both are same actually. Determinant of the coefficient matrix, and that's why we mentioned like that. Okay, and now in the next thing, first of all you just analyze from the Cramer's method side. In Cramer's method, what is delta 1? I am just recalling that delta 1. Delta 1 is simply nothing but replacing A1, A2 with C1, C2. This constant matrix as we discussed in the last class. Okay, if you are familiar with that, you will feel some comfortable, right? We need to replace this A1, A2 with C1, C2. If you replace A1, A2 with C1, C2, then that determinant of delta 1 will become 0 here, okay? Because B1 C2 minus B2 C1 0 here. Look there. B1 C2 minus B2 C1 is 0 here, but here it is not is 0, here also not 0. So if you analyze in such a manner, in this case again delta 1 is equals to 0, in this case delta 1 not equals to 0, here in this case also delta 1 not equals to 0. Then coming to delta 2. Delta 2 is simply nothing but the first column is just like A1, A2, but the second column is C1, C2. That means we need to compare A1, A2 with C1, C2. If you analyze A1, A2 and C1, C2 again, what you say? Again A1 by A2 is C1 by C2. Here you will get that delta 2 is 0, and here in this case delta 2 not equals to 0, and here in case delta 2 not equals to 0. Just analyze the situations, okay? See, if 3 delta, delta 1, delta 2 are not equals to 0, it has unique solution. If 3 are equals to 0, it has many solutions. And if delta is 0 and the remaining 2 are not 0, then we say that the system has 0 solution. And this is the discussion from Cramer's method side, okay? Whereas if you think from the matrix inversion method, in the matrix inversion method we are thinking about adjoint A into B. Okay, see what happens for adjoint A into B. Adjoint A into B, what will happen for it? Adjoint A into B, okay, and adjoint A into B. See, you just simply find that adjoint A into B as we discussed in the last class, and from this analyzation, since these two are not equals to 0, adjoint A into adjoint B is not equals to 0. And here again adjoint A into adjoint B is not equals to 0. And in the last case adjoint A into adjoint B is equals to 0. And this is the discussion from matrix inversion method. excuse me. So at the end we have different restrictions. If this system of linear equations in two variables have one solution, algebraically we say these ratios are not equal. From matrix inversion method side we say that delta is non-zero, adjoint A into B is also non-zero, and from Cramer's method side the restrictions are all the delta 1, delta 2 are non-zero. Okay, then if this system of equations have zero solutions, algebraically we say these two are equal and which is not equals to C1 by C2, and the restrictions from the matrix inversion side, delta is determinant of A is 0, adjoint A into B is non-zero, and restrictions from the Cramer's method side, delta is 0 and the remaining two, delta 1 and delta 2 are non-zeros. Okay, and if the system of equations have many solutions, algebraically these three ratios are equal, and from matrix inversion method side these two are zeros, and from the Cramer's method side delta 1, delta 2, 3 are zeros. Usually if we have a system of linear equations in two variables, we will go with this algebraic forms itself. Okay, once again I am repeating, if we have a system of linear equations in two variables, we generally solve the problems using these algebraic techniques, but we need to extend it for the equations of three variables. Okay, analyzing and generating certain rules and restrictions in system of linear equations in three variables is bit complicated, and that's why here itself I am generating certain restrictions related to the matrix inversion method and Cramer's method, and the same analysis I will extend it for the linear equations involved with three variables, and that's why I mentioned all these things. Okay, just have a note, go for a screenshot. So look at the board. These are some simple problems related to the linear equations in two variables. See, first one you need to solve using a matrix inversion method, and second one just solve by Cramer's method. Third one you need to find the number of solutions without solving. And D, see, you need to find the value of k if the system of equations has infinite solutions. All these problems are somewhat simple. You just try them and then comment your answers, right? And that's for today's class.